Okay, let's start ACM Multimedia 2020 tutorial on effective and efficient toward open world instance tree identification. This talk is about a billion scale approximate nearest neighbor search. I am Yusuke Matsui from the University of Tokyo.
So the task here is nearest neighbor search, NN. So given the n d-dimensional database vectors xn, n equal 1 to large n, so like this. Our task here is like this. Given the query vector q, find the closest vector from the database, like here. So mathematically, it's defined like this: q minus xn, and this is distance function, and we will find the minimum items. Then in this case, x74 is the most smallest one, so it's similar to this one. So this is one of the fundamental problems in computer science. So the solution here is, of course, linear scan. It is a linear cost of the number of vector n, so it's slow if n is large, right? So we need a faster method. Okay, so then this tutorial we are considering approximate nearest neighbor search, ANN. So it's a much faster search, and it doesn't necessarily have to be exact neighbors. So there's a trade-off: runtime, accuracy, and memory consumption. So this is an approximated version of nearest neighbor search. So this is a sense of scale. So in this tutorial, we are considering billion scale data, and everything is on memory. So like this, so dimensionality is 100 or something. The number of items is 10 to 6 to 10 to 9. And the memory consumption is like 32 gigabyte RAM, so it's a usual computer level. This runtime is like 10 milliseconds or something, so millisecond level, right? This is a sense of scale. So why nearest neighbor or approximate nearest neighbor search is used for computer vision? The direct application is, of course, image retrieval. So if an image is represented by a feature vector, then finding similar feature vector means finding similar images, right? So we can use that for image retrieval. Takuma will explain this image retrieval in the next tutorial. Another example is person identification. So here the task is finding the same image, same person from the images. So Jen will present this talk in the next section. Okay, another example is clustering. So if we consider k-means clustering, for example, we need to create a distance matrix. That is essentially a nearest neighbor search. Another example is, of course, KNN recognition. This is also a direct application. Then, if we see the history, so why computer vision people developed nearest neighbor search? That is because it was used for fast construction of bug feature representation. So this is a history. So one of the benchmark is still SIFT feature vectors. Okay. So this is the most important slide of my talk. This is a cheat sheet for approximate nearest neighbor search in Python as of 2020. So I will explain later details, but if you follow these lines, then you can find the best algorithm for your data. So this is again, don't forget, this is the most important slide of today's my talk. Okay, so this tutorial consists of two parts. First part, I will introduce a nearest neighbor search, so exact nearest neighbor search. And the second part, I will introduce an approximate nearest neighbor search. So let's start with the first one, nearest neighbor search. So again, this is a picture of our problem. So first of all, you should try this nearest neighbor search, so without approximation, because recent libraries are really fast. So I first introduce a naive implementation, then introduce a fast implementation. That is from Face library from Facebook AI Research. You'll see many times in this my tutorial today, because it's super fast. And I want you guys to experience the drastic difference between two implementations. Okay. So this is a problem. Let's say we have m d-dimensional vectors, query vectors, like q equal q1 to qm. So in this talk, we suppose that there are many query vectors, and there are n d-dimensional database vectors. So this is database. So x1 to xn. So m equal n equal much larger than m here. So our task here is given query vector and database vector, so compute a distance function. So here our distance is a squared Euclidean distance, for example. Then this is a naive implementation. This is a pseudocode of like Python plus C++. But anyway, given Q and X, the naive way is of course first define difference at 0, and we iterate or dimensionality and taking minus, so difference of each element, and squared and sum them all. This is difference, so L2 square function. Then our task is computing all combinations, so we run 2 for loops. The first for loop is for query, and usually we parallelize the query side here, so we don't use parallel algorithm inside here. Then for each query, we compute each database vector, then compute L2 square distance. Then we need to select a minimum item by heap, but we just omit now here. So this is a naive implementation, right? Okay. So next I will introduce a much faster implementation of phase. Very interestingly, a phase switch algorithm, 2 algorithms. If m is less than 20, so m meaning that the number of query vectors, so phase compute this distance by SimD. In other cases, they expand this equation by like this, then compute everything by BRAS. So it's a kind of interesting switch. So I will introduce one by one. First I will introduce this one. Okay, so this is a computation of x minus y by SimD. And this is actual code, actual SimD code. And this is a reference. So this code is now written like here. Okay, then this is an example. So let's say x equal 31 dimensional vectors, and y is also 31 dimensional vectors, and each element is float 32 bit. Okay, so how to compute this very quickly? So they use SimD. SimD is like a special register to compute everything at once. So in this case, they prepare 256-bit SimD register mx and my. So by using these registers, we can process 8 floats at once. So in this case, they first read first 8 element of x to mx and the first 8 element of y to my. Then taking minus at once. So this operation is just one operation. Then they are taking a multiplication. So this means they compute a difference, right? Then stack that. Then let's iterate that. So next here, next 8 elements are read here and read here. Then the same manner, they compute difference, they compute multiplication, and they plus equal, so they sum them all. Okay. Then here, so there are no 8 elements here, so they take sum of first 4 elements and last 4 elements. Then they store them on a 128-bit SimD register. Okay. Then in this part, they do the same thing for 128-bit register, SimD register, like here. So everything is just 4 elements. Okay. Then finally, it's last. So the rest, so they pad 0 here, 0 here, then do the same thing. Okay. So finally, sum them all, then we can get the result. Okay, so this is a SimD implementation of Euclidean square distance. The interesting thing here is SimD code of phase are very simple and very easy to read. So it's really nice to study. So being able to read SimD code comes in handy sometimes. So why this implementation is super fast. And another example of SimD register, SimD L2 square is you can find that here. Okay. Okay, then we finish this part. Then let's move to this one. So BRAS thing. So here we compute this function equation by BRAS. So we first stack m d-dimensional query vectors into a d times m matrix here, Q, big Q. And in the same manner, we stack database vectors like x, right? So we first compute a table like Q norms equal norms Q. This norms function is also a SimD accelerated functions. And this is like this. For each query vector, they compute the norm, Euclidean norm. and the same here. Then here, inner product, we compute inner product between Q and X like this, Q transpose X by a Brass function. So this is a matrix multiplication by Brass. So as you can see, if the number of query vector is large, then this part is dominant, like if Q and X are large. So they use this algorithm if Q is large. Interesting thing here is the difference of the background matter. So intermass scanner library is 30% faster than OpenBRAS. But anyway, this is Brass function, so it's super fast. Then after that, they scan and sum. So parallel 4 for the query side and 4 for the database side. Then each distance is computed just by fetching item m and fetching norm and fetching norm and inner product, right? So this is same as this part. Okay, so by using that, they use like matrix multiplication to compute nearest neighbors. Okay. Then finally, I need to say that actually, so GPU is much more faster than CPU. So Face provide a GPU implementation as well, and that is super fast. So it's in a GPU they always compute this expanded version. So there is a benchmark for k-means. So k-means is a nice benchmark for nearest neighbor search, and from there this benchmark. So CPU takes 11 minutes, and it's 10 times faster if we use P100 GPU here. It's faster if they are using multiple GPU or float 16 or something. So if a GPU is available and its GPU memory is enough, then you should try GPU nearest neighbor. And please be careful that the behavior is a little bit different. Okay. So this is the reference. Okay, so the first part, nearest neighbor search, is finished. Then let's move to the approximate nearest neighbor search. Okay, so this is a summary of approximate nearest neighbor search. I summarize the nearest neighbor search algorithm into 3. So first, these two are million scale data. So meaning that the number of database items is million level, 10 to 6. And this one is 10 to 9, so it's billion level. And for million level, I'm considering this one is the methods which use raw data, original data. So that accuracy is good, but of course memory consumption is not good because they need to store original data. And this right side one is a compression method. So the original data are compressed in some short code. So the accuracy is not good, but memory it's very memory efficient. So these are two methods. Then for billion scale method, the only way we can do is using inverted index plus data compression. So first we divide the space into some small regions, and for each region, so items inside this region is stored as a posting list, like here, with the data compression scheme. So this is the only way we can do. Okay, I will introduce one by one. So first, I will introduce locality sensitive hashing. Locality sensitive hashing is maybe one of the most famous and well-known method for approximate nearest neighbor search. So it's a set of hash functions plus hash tables. So they map similar items to the same symbol with a high probability. So in a recording phase, if we like to record X13, for example, then we put this into a hash functions, then get a symbol. So this is a hash table with entry is this one. So we use this symbol as an entry and put ID here, 13 here inside this. In the same manner, we compute another hash functions and take symbol and add ID here. So we repeat this type of operations. Then all IDs are inserted to these hash tables. And in the search phase, given the query vector Q, again we compute a hash function here. This is a symbol. Then we can see these associated items here. So they are the potential candidate for final result. So we take these. And in the same manner, we can compute hash table like this. So they collected this. So then we compare Q with these items by the equivalent distance. So this is post-processing. This is RSH. So what kind of hash function do we use? There are many methods, but generally speaking, it's a random projection. Okay. Then the good thing of locality sensitive hashing is that it's math friendly. So because everything is random process, so we can use mathematics to analyze their algorithm, and it's popular in the theory areas. But the disadvantage is that it requires a large memory cost, and we need several tables to boost the accuracy, and we need to store the original data on memory. And usually data-dependent methods such as product quantization are better for real-world data. So in recent computer vision papers, LSH has been treated as a classic method. However, in fact, so if consider a next candidate, we can do that in practical memory consumption. So this green one is I explained first things, but we can consider actually next candidate, next similar symbol. Then we can use this as a candidate as well. So this idea is used to create a Falcon library. Falcon is maybe one of the most famous LSH based library. You can install that by just pip. The good thing is it's faster for data addition compared to other method, because we need to compute the hash function, just hash functions, and so it's maybe useful for on-the-fly addition. And parameter, the bad thing is parameter configuration is not intuitive. Okay, this is a reference. Okay, so I talked about LSH here. So next I will talk about the tree space partitioning method. Okay, so the most important, most famous method is basically maybe FLAN, fast library flag prosecution nearest neighbor search. It's this library automatically selects algorithm from a randomized KD tree or k-mean tree like this. So these tree-based methods are basically KD tree type of thing. So recursively divide the space into some small space, then run search. So this library is good in terms of code. So it's a good code. So it's implemented in OpenCV or PCL, like famous libraries, and very popular like 10 years ago. The disadvantage is again, so it takes a large memory consumption because the original data need to be stored, and it seems it's not actively maintained now. And another tree-based method is annoy. It's like 2-min tree plus multiple trees plus a shared priority queue. In a recording phase, they select 2 points randomly, then divide a space, and repeat this step, and repeat this step. So we can create like tree type of things. In the search phase, given this query vector, we just see this cell, then compute the distance, compute the distance. So, because this is like tree, so we can traverse this tree by a log times comparison. Okay, so it's fast. So it's basically it's a KD tree type of method. And one feature is that if we need a data point, we can use a priority queue. So that's the same as KD tree. And another feature is if we'd like to boost the accuracy, then we can use a multiple tree with a shared priority queue. So we can prepare several trees and run search. Then we can merge this result like this. So this region is better than this each region. Okay. So this is annoy. You can install that by just pip. And this is the code. It was developed at Spotify. Now it seems it's very well maintained and stable. And its interface is simple, with only a few parameters. So, because it's very easy to use, so it's recently it is used for baseline of million scale data. An interesting thing is they support a memory map, so it can be accessed from similar processes. And limitation is again it requires a large memory consumption, and runtime itself is not so much faster than next method I will introduce. Okay. Okay, then tree-based method is finished. So again, we next move to the final method for raw data method. It's a graph traversal based method. Okay, so it's very popular in recent years. That is graph traversal method, because around 2017, it turned out that the graph traversal based method works pretty well for million scale real world data. So the pioneer is a navigable small world graph NSW, and its hierarchical version, hierarchical NSW, HNSW. So this is so super important, so please remember this one if you don't know. And there are many implementations. Okay, so I will explain this algorithm. So how to record data? So because this is a graph-based method, we need to create a graph. Please consider each node is a database graph, a database vector. So this blue one is, for example, x13. Let's say this is a graph of x1 to x90. So I will explain how to add a new vector here. Given a new database vector, we will create a new edges to neighbors, meaning that like this. So for this x91, so these three are closest vectors, so we can simply create edges here. Okay, and that's all. So we can repeat this type of process, then create a graph. So interesting thing is array links can be long, because in an array phase, so there are not so much vectors, so some vectors are far away from some vectors, but still we need to make a link. So such links can be quite long. And such long links encourage a large hop, making the fast convergence for such. So it's kind of interesting part. Okay, so the search phase. How to search? If we have a query vector here, so our task is finding the similar one. So in this case, this is a result. So how to find this one? So we start from a random point. We select random point as an entry point, like here. Then from the connected nodes, we will find the closest one to the query. So meaning that for this, there are three connected nodes here, these three, right? And we compute the distance between this one and the query, and this one and the query, and this one and the query, these three green lines. Then in this case, this guy is closest to the query. So we hop this one, like this. Then we'll repeat this process, like this. For this, there are some connected nodes, but this one is most closest to the query. So we hop this, then hop this. So we repeat this process. This is a search. Okay. So this extension is hierarchical NSW, HNSW. We can construct the previously explained algorithm by hierarchical manner. So this structure works pretty well for real-world data. So for example, this is a finest level graph, and we can subsample some of them, for example. Then we start to search on this coarse graph, like here. Then move to the same node on the final graph, then we can run search again. So by repeating this process, we can run search in a hierarchical manner. Okay. So this is a library NMSLib, metric space library. This library contains a lot of methods, so you can find the method, especially HNSW is here. So this HNSW option is the best method as of 2020 for medium scale data, and it provides a simple interface. So if memory consumption is not a problem, you should try this one. So again and again, the disadvantage is that it requires a large memory consumption. And another thing is data addition is not fast here. Okay, so since HNSW is super strong, so there are two other implementations. So this library, HNSW-lib, is a spin-off library from the NMSLib I explained in a previous slide. So this includes only HNSW, so it may be simpler, so you can use it if you wanna extend this algorithm. And this is a face again. Face also implement HNSW. Okay. Then graph-based methods are very strong, so there are many other graph-based approaches. So from Alibaba, they provide this graph-based method. And from Microsoft Research Asia, they also provide this kind of method. They said that it's used inside Bing. And from Yahoo Japan, they provide another graph-based method, NGT, and this one is actually strong. So this NGT and NMSLib are fighting each other for the benchmark. Okay, this is the reference. Okay, so I explained this medium scale method and method which use original data. Then I will move to this compressed data method. So in this method, so each vector is compressed to some kind of short code. Okay, so I will start to explain this. Okay, the basic idea here is that we convert n-dimensional feature vector into some form of shortcode, right? Because for this data, we need at least 4 ND bytes to represent these vectors. because if each element is 32-bit float, then that means 4 bytes. So 4 ND is must require, of course. So if n or d is too large, so we cannot read all of the data on memory, because, for example, if d is 100 and n is equal to 10 to 9, then it takes just data 500 gigabytes, so we cannot read everything. So the idea is to convert each vector to a short code. And we design a short code such that memory is like efficient. For example, if this one code takes just 32-bit, then these data can be represented by just 4 gigabytes. Okay. Then we run search for a short code world. So what kind of conversion is preferred? So the distance between two codes can be calculated, computed. For example, these two Hamming distance between these two codes can be computed, and that distance can be computed quickly. And that distance approximates the original distance between the original vectors. For example, L2 squared distance between two vectors approximated by the Hamming distance between two codes. And sufficient small length of code can achieve the above 3 criteria. Okay, this is basic idea. Then I explain two methods: a lookup-based method and a Hamming-based method. And a Hamming-based method is like this. So each feature vector is converted to a binary vectors, like b-bit binary vector here, and its Hamming distance can be computed, and it approximates the original vector. There are quite a lot of methods actually, so please take a look at the survey paper if you have interest. And this is not the main scope of this tutorial, because PQ is usually more accurate in terms of accuracy for nearest neighbor search. Okay, then I'll move to lookup-based method. This is product quantization. Okay, product quantization, PQ. This method is very simple. So we split a vector into sub-vectors and quantize each vector. So in this case, our task is this one, vector, d-dimensional x vector, to compress this to some form of short code, PQ code. Okay, to do that, we need to prepare a code book, and that is trained beforehand by running k-means on the training data. So in this case, two-dimensional 256 vectors, and the same one and same one here. Okay, then what should we do? So you first split this vector into 3 parts in this case. Then from the first two-dimensional vectors, we find the closest code word here, from here. In this case, this ID2 is the most similar. Then we just record just this ID2. So we just record an integer here, and do the same thing here, and do the same thing here. And that's all. So this is product quantization, and it's very simple and very memory efficient, and the distance can be estimated. I will explain later. So it's just running a vector quantization 3 times in this case. So one thing is this is bar notation here. So given a d-dimensional vector, we represent the bar to say PQ code. So this, if you see bar, that means this is PQ code, like a set of integers. Okay. Okay, so first I will explain why it's memory efficient. So as I said, if one element is float, 32-bit, then the original vector is, for example, if d equals 128, then it takes 4000 bits. On the other hand, the PQ code, so usually this ID is designed like small integer. So we need just one unsigned char, 8-bit, to represent the data. So if m equals 8, this is a typical situation, then it takes 64-bit. So the whole data is 64 times memory efficient. Okay, so this is memory efficient. And the distance estimations, we can estimate distance we can estimate the distance. It's a kind of interesting property. So this is query vector, for example, and they are database vectors. So our task is find the similar vectors from database vectors, right? So first we apply product quantization for the database. Then we can get this PQ code. So again, each PQ code is just a set of integers, small integers. So it is not obvious how to compute the distance between Q and each PQ code, because this is just an integer, so we cannot compute the distance. However, dqx square dqx can be efficiently approximated by daqx bar. So this is asymmetric distance. And this is PQ code. So we can approximately compute the distance between this one and this one. So by using lookup trick, we can look up some pre-computed distance table, then we can compute this one. Anyway, so the important thing is we can linearly scan each item. So this one, this one, this one, this one, this one, this one by DA. So we can compute it. We can run a linear search here. Okay. So this is a code. This is not pseudocode. This is actual Python. So because PQ is super simple, so it's only tens of lines is required for Python. And you can see this is a pure Python library, NanoPQ. You can install this one to check these algorithms. Okay. And there's a deep PQ also available. So deep PQ, they it's actually supervised search. So they use a label. So it's different from the original PQ, which is an unsupervised method. So this consists of base CNN plus PQ like layer plus some loss. So they need class information anyway. The recent papers are considering how to compute PQ for like deep architecture. Okay. And if you have interest, you can please take this survey paper. They provide a much more comprehensive survey for PQ. This is a relation between Hamming-based method and looking-up-based method. So actually, they are kind of a brother relationship. So if you have interest, please take a look. Okay, then we finish a million level topic. Then now let's move to billion level search. So again, it is an embodied index plus data compression. So first, we need to divide the space into some small subspaces because it's super large space, large data point are here. Then for each subspace, there are many points. Then we use PQ to compress such data and store that as a posting list. So this is a general strategy to handle billion scale data. Okay, so this is a recap. Please remember the original vector can be converted to PQ code, and I use bar here. And if we have Q and X is quantized to X bar PQ code, then our task QX or DQX can be efficiently approximated by X bar, like here. So the distance between original vectors can be approximated by PQ code and query. Okay, so that's please remember this one. Okay, then let's introduce a billion scale search. So embodied index plus PQ. So first we need to prepare a cost quantizer like this. So this splits a space into k subspaces, and this C is a centroid, and they are created by running k-means on the training data. So it's a k-means, and these are center vectors. Okay. Then let's introduce how to record data as x1 here. So how to record that? So if this one is in this C2 area, then if C2 is closest to x1, then we compute the residual R1 between x1 and C2. So R1 equal x1 minus C2. So that means this green arrow here. Okay. Then we quantize R1 to R1 bar like this. So we quantize this vector by using PQ. Then we record this with the ID 1 here. That means we record I and Ri bar like this. So I is ID here, in this case x1. Then Ri bar is this PQ quantized residual. And this is how to record data. Okay. Then we repeat this process for all database vectors. So for all vectors, we record ID and PQ residual as a form of posting list, like this. So this is a basic data structure for embodied index plus PQ. Then how to do search? So given the query vector, our task is to find the nearest vector to Q. So again, if this Q is here in the C2 region, then we compute the residual again, RQ equal Q minus C2. right? Then we check this region, item in this region. That means k equal 2. So if we see this posting list, there are 2 items here. So we compare these items to Q by using residual. So for example, we compare Ri with Rq. That means that this one is our final. We want to know this distance, right? Q and xi, and we can use some simple math. If we subtract C2, this is a constant vector, then it's the same as RQ, Ri. That means that the distance between the original vectors are same as the distance between residual vectors, right? So this can be approximated by dA, so RQ and Ri bar, the PQ code, right? So here PQ code and query residual. So we can find compare these two vectors. So by scanning these, then we can get we can find the smallest one. And there are many strategies here. But anyway, this is a way to find run the search. Okay, so finally I will introduce our face. This is the strongest library maybe in the approximate nearest neighbor search. It's created from the original authors of the PQ and a GPU expert at Facebook AI Research. So there are 2 versions, or CPU versions, that all PQ-based methods are implemented, and GPU version that some PQ-based methods are implemented. And the bonus here is nearest neighbor search is also implemented, and it's quite fast, as I explained earlier. And k-means is also implemented. That's super fast. So in terms of programming, what I explained previously here is written here. So we first define cause quantizer here, but this is actually exactly the same as simple linear scan. We can create simple linear scan in expert L2 and set as quantizer. Then we construct the whole inverted file, so inverted data structure with PQ. And then here we put this quantizer as an input. So here select a cause quantizer. Then some parameters are here. Okay, then this is a thing. Then we can train and record data and search parameters and such. Right? It's a kind of very intuitive from this figure. Okay. Okay, finally, I will introduce the state-of-the-art fastest method for billion scale data. The point here is this part, space partitioning, is actually this part itself is nearest neighbor search, right? So we can use the fastest nearest neighbor search method here. That means this graph traversal method. So we use these for this space partitioning. Okay. So this is the thing. So this part is replaced by a graph-based method, HNSW. So each blue dot is a centroid, right? So if we write code, like here, so now quantizer is not nearest neighbor search, it's a HNSW, so it's index HNSW flat, right? Then we use these for cause quantizer here. So it's very easy. We can easily switch a cause quantizer from linear scan to HNSW. And this is the best approach for billion scale data right now. And this structure is a backbone of a recent state-of-the-art method like these two. Okay. So the advantage of face is that it's from the original source of PQ, so it's extremely efficient in terms of both theory and implementation. And there, it's used in a real-world product like Mercari. And for billion scale data, face is the best option, I think. Now, especially large batch search is fast, meaning that the number of query is large. Disadvantage is that the documentation is not enough actually, especially Python binding. And since there are a lot of methods, it's hard for a novice user to select the best algorithm. And currently, Anaconda is required, so PIP is not officially supported. Okay. This is a reference. Okay, so finally, we come back to this cheat sheet for an approximate nearest neighbor search. So we start from here. First, let's check so you have GPU or not. If you have GPU, so please try a face GPU linear scan. Then if your GPU memory is not enough, then you can try an approximated version of IBFPQ, so GPU IBFPQ. And if it's still out of memory or its accuracy is not enough, then going back to CPU, then try CPU linear scan. And if you think it's slow, then please try HNSW by either NMSLib or phase implementation. And if you like, you can switch these algorithms. Then if this is still slow or it's out of memory, then you can try this CPU and HNSW plus IBFPQ. Then if still it's not enough, then you can change parameters like here. Okay. So, and one thing is that, so in this talk, so we assume that D is like 100. So if D is much larger, then please run PCA. Okay, so this is a cheat sheet. Okay, finally, I will show some random topics about nearest neighbor search. The first one is benchmark. So there is an AN and benchmarks. It's this repository. It's super popular. It's provide a comprehensive and thorough benchmark for various libraries, and it's Docker-based isolation, so it's super. It's really extensive. And its top right is better, so meaning that the method is here and better. And currently, NMSLib and NGT are competing each other for the first place. They are fighting. So this is really include a lot of methods, so you can try this. And this is another benchmark. It's much more lightweight and easy to use. So it's just running some Python lines, then you can render this kind of image. And the interesting thing here is this library implemented multi-run. So multi-run meaning that so running all algorithms on the all dataset at once by using this Hydra library. Okay. And another topic is trillion scale search, n equal 10 to the 12, so 1 tera. So the sense of scale is that if it's k level, it's just in a second on local machine. If it's m, then all data can be on memory. So we can try similar approaches. If it's g, then we need to compress data by PQ, and only 2 datasets are available, right? So if it is t, so we cannot even imagine what's happening. So only phase wiki, so there's a discussion about 1T vectors. Do they use distributed or memory map or many other techniques? Now, interesting thing here is this is a figure from this wiki, and they are discussing with a sparse matrix of 15 extra element. So it's super huge. Okay. This is also a very interesting topic. So recently, many people try to develop a nearest neighbor search engine. That is something like ANN plus SQL. And algorithm itself is phase or NMSLib or NGT or something. But many companies try to create these search engine for using nearest neighbor search. So it's provide a lot of function. It's practical functions like distributed system or data deletion or something. Okay. And finally, I introduce some problems of nearest neighbor search. So one thing is no mathematical background. So currently, only actual measurement matters, so recall on runtime. Nearest neighbor search problem was originally mathematically defined 10 years ago, but recently no one cared about this definition. So when the score is high, so it's not clear the reason actually. So the method itself is good, or the implementation is good, or the method just happened to work well for the target dataset. So it's not sure. And the difference of library matters, for example. That's one example. So if one can explain why this approach works good for this dataset, it would be a great contribution to the field. And not enough datasets. So currently only 2 datasets are available for billion scale data. So new and diverse dataset would be good for the field. Okay, so finally I will show you this cheat sheet again, and then this is the end of my talk. So thank you.
Okay, let's start. This is CVPR 2020 tutorial on image retrieval in the wild. Billion scale, approximate nearest neighbor search. I'm Yusuke Matsui from the University of Tokyo.